Hello and welcome to another Common Core Geometry lesson by eMathInstruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson number 6 on Reasoning with Similarity. Alright, the word reasoning should give you kind of a key that we're going to be doing a little bit of proof work today, a little bit more in terms of just explaining our reasoning and using similarity criteria to prove that triangles are similar to one another. And we're going to need that going forward in the course when we do other things with similarity, things that are kind of subtle, especially when we get into circle geometry. Let's launch right into the lesson though, okay? And let's recall the similarity criteria from the last lesson, all right? Specifically, what do we need to know about two triangles in order to know they're similar? And what we have is we have three theorems that tell us that. Angle, angle, side, 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 and side, angle, side. If you weren't with me for the last lesson, one thing that I tried to emphasize a lot was that the most important of the three undoubtedly is angle, angle. Now don't get me wrong, we'll also see side, 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 and side, angle, side on occasion, but the primary way that we will prove that two triangles are similar is by showing that two angles of one triangle are congruent to two angles of another. Remember, the side, 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 and side, angle, side, specifically when you see the word side, it doesn't mean that two sides are equal. It means that you've got, in this case, three pairs of sides that are in proportion to one another, and in this case, two pairs of sides, and the angle between them being equal. So let's see how that kind of pans out. All right, oh my goodness, we haven't seen a t-table proof for a little bit, so let's take a look at this problem. Exercise number 1. In the diagram shown, BD and AE are drawn and intersect at C. It's also known that AB is parallel to DE. Prove that triangle ABC is congruent to triangle EDC. All right, so I want to prove that the triangle up here is similar to the triangle down there. And I want to use one of those three theorems to do it. All right. Now, we should always be, as I say, kind of biased towards the angle-angle theorem because it will come up the most often. Now, you know, I can definitely use different types of angle names, but I'm going to label some angles with some numbers right now. Okay. And I'm specifically going to label all of those. Now remember, I just have to establish if I'm going to use angle-angle that two pairs of angles, or that two pairs of angles of one triangle are equal to two angles of another triangle. Think about this for a second. I actually have kind of a plethora of different angles I can prove are equal. One thing I can say almost immediately is that angle 3 and angle 4 are equal because those are vertical angles. I also know that angle 1 will be equal to angle 2 because they're alternate interior angles that are created when a transversal cuts across two parallel lines. Now, if you're kind of on your toes, you might also say, well, what about this angle up here, angle B and angle D? Aren't they also equal for the same reason? And the answer is yes, yeah, they are, and you could go ahead and use those as well. I'm not going to. I'd like to get a little vertical angles into the mix because they oftentimes come into play when we talk about similarity proofs. All right, but let's lay it out. It's going to be this simple. AB is parallel to DE, and of course, that's my given, right? I knew that, all right? So then angle 1 is congruent to angle 2. Why? Because alternate interior angles created by parallel lines crossed by a transversal are congruent. Now keep in mind what you don't want to say in a situation like this. You don't want to say something like definition of alternate interior angles, or just alternate interior angles. Perhaps you could get away with just saying alternate interior angles are congruent. Better to say alternate interior angles created by parallel lines are congruent because, again, you could easily have two lines that are not parallel, and then your alternate interior angles here and here would not be equal. Okay, they wouldn't be congruent. I'm going to erase that because we don't need it. Let's get that angle 3 congruent to angle 4 because vertical angles are congruent. Finally, triangle ABC must be congruent to triangle EDC. Oh, no, no, no. No, no, not congruent. Must be similar to triangle EDC by the angle-angle similarity theorem. Sorry about that. Definitely not congruent. You can tell they're not congruent. This one's a smaller triangle than that one. Now again, if your urge is to get angle 1 congruent to angle 2 and angle B congruent to angle D, One thing that's nice about that is you can use the same reasoning. They're alternate interior angles created by parallel lines, so therefore they're congruent. that's fine. But I've got to get two angles in this triangle congruent to two angles in that triangle in order to say that the two triangles are similar. I'm so used to congruent that I just want to throw that congruence symbol in there. Anyway, let me step back, have you take a look at this, and then we'll move on to another piece of reasoning. All right, let's do it. Okay, have you think about this a little bit. Exercise number 2. In the diagram shown, MN is congruent to MP. Typically in a larger diagram like this, I'll often symbolize that kind of like that, maybe even put a couple dash marks like that. And points R, S, T, and W all lie along the sides of MNP such that RT is perpendicular to NP and SW is perpendicular to MP. Let's mark that. Let me put a little right angle there, little right angle there. Explain why triangle NTR must be similar to triangle PWS. So why does this right triangle have to be similar to that one? Pause the video now and see if you can write out maybe a paragraph proof on why those two triangles must be similar. All right, well, let's talk about it. Let's kind of sketch out the proof. Actually, maybe we'll start writing it out. Remember, again, if I'm going to use angle, somehow I've got to prove that there's two angles in this triangle that are equal to two angles in that triangle. All right, well, one angle that I can see immediately equal is that 90-degree angle. So let's just say this. Because RT is perpendicular to NP and SW is perpendicular to NP, okay, angle RTN is congruent to angle SWP because both are right angles. All right. So that gets us one angle pair. But how do I get the other angle pair? Did you figure that out? Well, we can get another angle pair by saying angle N is congruent to angle P. Now, why do I know that? Well, angle N must be congruent to angle P because the base angles of an isosceles triangle are congruent, right? And why do I know that this is an isosceles triangle? Well, it comes from that. Anytime you're told that two sides are congruent, if they're two sides of a triangle, then the angles opposite those sides, so this side is congruent to that one, and therefore the angles, those base angles of an isosceles triangle, are congruent. But that's it. Angle congruent to angle, angle congruent to angle. I can now say triangle NTR is similar to triangle PWS by the angle similarity theorem. All right, that's cool. This smaller right triangle, or sorry, this larger right triangle, similar to this smaller one. Now, let's do a similarity problem. All right, not a proof, but a problem. So now, we know that these two triangles are similar, all right? And I'm going to actually draw them separately. Okay, we have RTN and beautiful picture, SWP. We're told that RT is 12 and PW is 3 and SW is equal to NT. So they're telling me that this length, SW, is equal to this length, NT. Maybe I'll call them both X. All right, since I need to solve for the length of SW, call them both x. So now think about these proportions we can set up, right? I can say that 12, right, larger triangle is to smaller triangle, as larger triangle is to smaller triangle. Okay, make sure you really understand where that came from. 12 divided by x equals x divided by 3. Oftentimes teachers will say 12 is to x as x is to 3. Now be careful here, right? We haven't done a lot of quadratic algebra in this course, but x times x, remember, is x squared, not 2x. Okay, absolutely bad if you say 2x. Maybe we'll even take a look at that in a second. But I get x squared equals 36. Take the square root of both sides, and I get x equals 6. Now, it's very easy to check to see that's right. I'm going to just put a little 6 here, put a little 6 here, because 12 divided by 6 is 2, and 6 divided by 3 is 2. That proportion stayed the same. Think about how much trouble I'd get into if I did this and I got 2x is equal to 36. Then x would be equal to 18, right? I'm just going to write this down here. These are wrong answers. And that would be very weird, because then somehow this side would end up being longer than that side. Clearly it's not. Now I know I shouldn't necessarily base things on what the picture looks like, but if these are similar triangles, right, then 12 to 18 is not 18 to 3. It's just not the right ratio, all right? So check when you can in those types of problems. All right? Kind of bring this up a little bit and give you a chance to copy down anything you need to. All right, let's move on. Exercise number 3. In the diagram shown, midpoints of sides AE and AD have been marked as C and B and connected to form segment BC. Draw a sketch of triangle ABC and ADE separately. All right, so why don't you go ahead and do that. Draw pictures of ABC and ADE separately. They don't have to be perfect, all right, but try to make them look like they're similar triangles. All right, well, for me, there they are. I literally just took them out and reproduced them. All right, so there are my two triangles. Now, letter B asks, what angle must be congruent between the two triangles, and why? So if I just have these two triangles, I don't know yet that they're similar. They're going to turn out to be similar. I don't know yet that they're similar, but I can definitely say, this angle and this angle are equal. Which two angles can I say are equal? Well, of no great surprise, their shared angle is equal. Let me kind of bring this down. So angle A is congruent to angle A because it is a shared angle. All right? It's a shared angle. It's the same angle, right? It's that guy right there. Okay. Now, the problem says, why can we use side angle side to justify that these two triangles are similar? Well, I know I've got the angles, right? So now, why can I use side angle side to justify that the triangles are similar? And maybe for this, we need to really go back up to the original picture. So why is that? Think about that for a minute. And by the way, as a hint, it has something obviously to do with this. So let's talk about it. Well, because C and B are the midpoints of AE and AD, well, what would we know? We would know that AE divided by AC equals 2, and AD divided by AB is equal to 2. You could also flip these ratios and say that they're both equal to 1/2. But that's the deal with side angle side, right? The two sides are, I've got two pairs of proportional sides, so two pairs of proportional sides and, not angle yet, and the included angle equal. Or congruent, right? And it's hard to mark that up on a diagram, all right? But again, the idea of side angle side is that whatever the ratio of this side to this side is, must be the same as the ratio of this side to this side. And because C and B are both midpoints, right? They're really kind of sitting right about here. Because those are midpoints, right? Then what I know is that the length of AD has to be, or sorry, AE has to be twice the length of AC, and the length of AD must be twice the length of AB. All right? Finally, letter D, why must EDA, right, which is this angle, why must EDA be congruent to angle CBA? Why must those two angles be congruent? And what does this tell you about ED versus CB, and why? So 2 questions here. Actually, maybe 3 questions. All right, well, the answer to the first question, why do those 2 angles have to be congruent? Because corresponding angles in similar triangles are congruent. All right? They're corresponding angles in similar triangles. They're congruent. Now, what do those 2 angles being congruent tell you about this side length and this side length? This tells us that ED is parallel to CB because a pair of a pair of corresponding, there's my red pen, angles are congruent. Right? That whole business where if I've got 2 lines crossed by a transversal and a pair of corresponding angles, angles in the same spot, are equal, then those 2 lines have to be parallel. Believe it or not, this goes all the way back to a problem we did back, I believe it was in Unit 4, maybe it was in Unit 5, when we were looking at quadrilaterals and parallelograms, and we specifically looked at what happened when you connected the midpoints of 2 sides of a triangle. You always ended up with a third length, this segment, that was half the length of this one and ran parallel to it. Back then, we didn't use the idea of similarity to prove that. We actually used properties of parallelograms, but here we see the same thing popping out in similarity, which makes some sense. All right? Okay, one last problem. Ooh, tricky diagram. Let's take a look at this one. Exercise 4. In the diagram below, parallelogram ABCD has point P located on side CD. Segments AP and BC are extended to point M where they intersect. Give an argument for why triangle MCP is similar to both triangle ADP and triangle MBA. Woo, wow. Okay, so first things first, you want to make sure in a problem like this that you really understand what 3 triangles we're talking about, right? So we've got triangle MCP, which is that one, right? I want to make an argument for why it's similar to both triangle ADP and MBA, which would be like that guy. I'm going to erase all that stuff in a little bit, all right? So we got to come up with this argument. What I'd like you to do is spend some time and think about it, okay? And don't forget, we're now working with a parallelogram here, and we know a lot about parallelograms. So take a little bit of time and think about why those three triangles have to be similar. All right, let's go through it. I need some angles here. All right, I don't want to use three-letter names, so I'm going to label a bunch of different angles. Okay, in fact, 5 of them. Okay, and let's start off with why triangle MCP is similar, to triangle ADP. You know, why is this triangle similar to this one? So let's start out with this. All right, let's talk about why angle 1 must be congruent to angle 2. Right? So I claim that angle 1 is congruent to angle 2. Okay, and I can make that statement because AD is parallel to MB, and angle 1 and angle 2 are alternate interior angles. Right? They're the angles of the Z created by parallel lines. Okay? But as well, angle 3 is congruent to angle 4 because vertical angles are congruent. All right? So what I can now say is that those two triangles, MCP is similar to triangle ADP, no great surprise, by angle. All right? Simple enough. Okay, so now why can I say as well that triangle MCP is similar to triangle MBA? Well, it's actually a very, very similar argument, all right? I can make it a little bit shorter, okay? Because I can say angle 2 is congruent to itself, all right? Now, why do I say that? Well, angle 2 is part of triangle MCP and triangle MBA. So I might as well use a shared angle. If I can get away with saying, hey man, this angle is congruent to itself by the reflexive property, all right, now I can also say angle 3 is congruent to angle 5 because, so this one, angle 3, is congruent to angle 5 because they are corresponding angles created by parallel lines. Thus, triangle MCP is similar to triangle MBA by angle. All right, by angle again. Okay, so parallelograms, due to the fact that they've got two pairs of parallel sides, give us a lot of information when it comes to angles. All right, and being able to have angles equal. The key here is being able to see that angles are equal. And again, there's other angle pairs I could have used. For instance, when we were talking about in the first set of triangles, MCP and ADP, I could have also said, let me change to green just so that you can maybe see it a little bit better. But I could have also said that this angle is congruent to this angle. Again, those being alternate interior angles created by these two parallel lines and that Z, right? You know, so there tends to be a lot of information, maybe even more than what you need to use AA to establish that two triangles are similar. All right, let me step out of the way for a second. You can write any of this down, and then we'll wrap up. All right, let's do it. So today what we did was we did a little bit of similarity proof, okay? And we saw how we could use angle-angle and side-angle-side. We never actually use side-side-side in these proofs. And it's going to be pretty rare that you would. I mean, we could probably come up with one, but quite frankly, it's more often the case that we will know that angles are congruent for whatever reason. Like in the last problem, we had a lot of parallel line properties that were coming out. Sometimes we have perpendicularity, which will establish that two right angles are equal. Right? It's way more common that you'll have that scenario than, let's say, knowing that 3 pairs of sides are in proportion to 3 other pairs of sides. Right? Now, don't get me wrong, you still need to know that criteria because it's one of the 3. All right? But it's not going to be used very often in proof. Side angle side is not going to be used very often in proof either. It's mostly going to be angle-angle. The question is, how do you establish that 2 pairs of angles in one triangle are congruent to 2 pairs of angles in another triangle? And we'll see that reasoning quite a bit as we move forward in this unit and in other ones. For now, I just want to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.